Hello and welcome to today's lecture on minimizing switched capacitance. This is the fourth lecture on this topic, and in my earlier lectures I have discussed about hardware software trade off, and we have seen that by replacing hardware by software we can reduce switched capacitance, particularly capacitance is reduced, leading to saving in power dissipation. And in the after that we have discussed bus encoding, where before sending some data over over the outside bus, it is encoded to reduce the power dissipation. As a consequence, particularly the transition activities are reduced by bus encoding. And in the last lecture we have discussed about clock gating, where we can introduce gating circuits in the clock tree to reduce power dissipation. Today we shall focus on finite state machines, and three techniques we shall discuss related to finite state machines, that is gated FSM, state encoding and FSM partitioning, and in addition to that I shall two more techniques, operand isolation and pre-computation. Let me start with finite state machine. As you know, finite state machines are integral part of digital systems. Whenever you go for synthesizing a digital system, it has got two parts, data path and control path, and essentially the control path comprises or is implemented with finite state machine. On the other hand, data path comprises ALU, registers, memory bank and so on, and control path is implemented usually by finite state machines. Now, if this is the model of a finite state machine I have already introduced. A finite state machine consists of a set of inputs Pi, the inputs are x 1 to x n, then it has got a set of outputs z 1 to z m P0, and a set of states S, and the set of states are S 1, S 2 up to S p, and there are two state transition function. Delta is the state transition function, and as you can see, next state is dependent on the present state as well as the present primary input, and similarly output transition can also be a function of the present state and the present primary input. So, we have also mentioned about two different types of machine. One is known as Milli machine, where the output transition is dependent both on the present state as well as the present input Pi as well as Ps. On the other hand, Moore machines are the output functions, output transition function is dependent only on the present state, not on the inputs. So, as it is shown here, this combinational logic to compute the output is dependent on the present state. On the other hand, next state is dependent of course on the primary input as well as present state. Now, whenever we realize a finite state machine, conventionally we apply a clock in each cycle to this latch, and the inputs as well as outputs are applied in each cycle. That means, as at each cycle there is some activation in these latches, activation of the latches and leading to transitions in inputs and outputs, and as a consequence there is power dissipation in the combinational circuit as well as in the latches or resistors. Now, let us consider an example 0 1 0 0 sequence detector, which I have already discussed. Here, as you can see, there are some conditions. For example, this condition, when the machine is in state S 1 and input is 0, there you can see as long as the input is 0, it remains in the state S 1 and output is also 0. That means, there are conditions when the next state and output values do not change, and similarly here there is another state S 4, you can see as long as the input is 1, it remains in state S 4 and output is also 0. So, you can say that we can consider these two as idle conditions, and in these conditions clocking the circuit during idle condition leads to unnecessary wastage of time. So, you can see the input and outputs are same. So, there is no need to change the input or the state, because output is remaining same, state is remaining same. So, the clock can be stopped if the idle conditions can be detected. So, this is the basic idea behind this clock gated finite state machines, and this saves power both in the combinational circuit as well as in the resistors and latches. So, this particular concept was proposed by Benini et al. In their paper. Now, I shall consider a specific case or a Moore machine. For a Moore machine, a self loop corresponds to the idle condition when the clock can be suppressed. So, a self loop like the one that I have shown can be detected, and in that case clock can be suppressed. So, here the self loop self FSI is equal to is when the primary input can be 0 or 1, such that the self FSI P I is equal to 1 if and only if delta x S I is equal to S I. That means, next state is S I and outputs also remain same, and P I is part of the primary set of primary inputs. So, you can find out a function f a, activation function f a, comprising all these self loop conditions where x I is the decoded state variable corresponding to the state S I, and that is all x I is 1 if finite state machine is in state S I. That means, if that is x I is 1 if finite state machine is in state S I. So, self S I, that is the self loop condition, captures all the set of input combinations for which self loop for a state is tougher. Now, what can be done? You can identify those self loop conditions, and then you can disable the clock during this period. So, you can apply a gated clock instead of applying this clock directly to this finite state machine. That means, both the primary input as well as the next state can be gated with the help of this and gated clock can be applied. So, this in this signal, this clock will not be applied when the finite state machine is in self loop, and this F A identifies all these self loop conditions, and accordingly it generates the signal here. So, it is enabled only when the machine is not in the self loop case, that means, clock is allowed to apply it. On the other hand, when this F A when the machine is in the idle state and self loop condition is identified, then clock is disabled. So, this is the basic idea behind this clock gated finite state machine. Now, let me illustrate this with the help of an example. So, here we have taken up an example of a timer counter which is interacting with a finite state machine. So, let us assume this is a timer counter. As you know, a timer counter counts down if some value is loaded in its register. There is an internal register where the count value is can be initialized, then it will do the countdown, and this is being interacted with a finite state machine. So, this is the FSM and it is interacting with this. FSM can be started with the help of a start signal, and FSM also generates two signals which is applied to this this timer counter. This is a timer counter. You can say this is a module, and these two signals are, one is your timer counter enable TCEN, and another is timer counter set TC set. TC set means timer counter set, this count value can be set. And this timer counter after this timer counter is enabled and TC is set, it will count down the value and it will generate a output when this countdown becomes 0. So, that is why it identifies a 0 condition, and that 0 is applied to this finite state machine. Now, it operates in this way. The output of the finite state machine is generated only when this 0 signal is received by the finite state machine, and it may really drive a large combinational circuit. Inputs are applied to this combinational circuit. This is a combinational circuit, and power dissipation in this combinational circuit can be reduced because only when this 0 signal is coming, then these inputs are applied to the combinational circuits, otherwise it is not applied. So, you can see lot of power saving can be done, and this finite state machine also is clock gated, as I have told. You will be applying clock gating to it, and this finite state machine will remain in the wait state as long as this countdown will take place. So, let us have a look at the state transition diagram of this finite state machine. It remains in the idle condition, and only when the start signal is applied, it goes to a state called set TC, and when the set TC state is reached, it generates these two outputs. This is a Moore machine. So, it outputs these two outputs to the timer counter. So, timer counter is enabled, and these two signals are applied, and these two signals will after this is done, the countdown will continue, and the machine will go to the this timer, and it will go to the finite state machine will go to the wait state. That means, you have applied a clock here, and a gated clock is also applied. So, that means, gated clock is applied to this finite state machine. So, this is the clock, which is applied to the timer counter, and let us assume the start signal is applied here. So, this is where the start signal is applied. So, start signal is applied, and that will in the next cycle, the finite state machine will go to generate this TC set and TC enable. So, at this point of time, the timer counter is enabled, TC enable and TC set signals are generated at this point, and now the countdown take place. This countdown can take place for a long time. So, you can see this can go on, and let us assume this is the point where the this 0 signal is generated. So, 0 signal is generated here, and so this duration is essentially the wait signal. And during this period, this clock is disabled and finite state machine remains in the idle state, and clock is also inhibited because this output signal is not generated. So, the output signal can be do it state. In this do it state, this is generated, and only when this 0 signal is received, the output signal is generated, that goes to the combinational circuit. So, power is saved here, power is saved in the FSM as well. So, this is being illustrated here. You can see the clock gating signal is generated with the help of a hardware FCG, which identifies the condition. That means, when the TC set is 0 and TC enable is 1. So, that is why TC enable and TC set, with the help of these two signals, an enable signal is generated, and that is loaded into this clock gating hardware, and this clock is not applied to the FSM unless the enable signal comes here. So, in this example, a state machine interacts with a timer counter that generates a long delay. So, this timer counter is essentially generating a long delay, that is the countdown period, and the FSM is clock gated during this long wait cycles. So, there is power saving in this finite state machine, and also there is power saving in this part of the circuit which the FSM is driving, because there is no transition here, and this clock you can inhibit the inputs to the succeeding stage with the help of this output. So, this is an example of a clock gating FSM. So, use of clock gated FSM provides power savings in the range of 10 to 30%. It has been found out by experimental results that this kind of power saving can be obtained by Benini and his colleagues. And the activation function f a itself may, however, as you can see, you are adding some additional hardware. So, this activation function f a itself may consume large power and outweigh the saving achieved using clock gating. So, this power saving that you achieved with the help of this clock gating FSM may be outweighed by the power dissipation of this activation circuit which generates FS. That is the reason why to realize FA, that is the activation function, it is recommended to select a subset of the ideal conditions such that these subset take place with high probability during circuit operation. That is, number one is this FA hardware should be small, and you have to see that these subsets, I mean this the occurrence of this phenomenon take place with high probability when the circuit is in operation. So, that is how you can achieve reduction of power in this range 10 to 30%. Okay. Now, let us consider another example related to finite state machine, that is finite state machine state encoding. I have already discussed about finite state machine and why, when and how state encoding is done. As you know, in the state assignment phase, each state is given a unique code, and state assignment strongly influences the complexity of its combinational logic part. And traditionally, state assignment has been used to optimize the area and delay of the circuit. As I have told in my earlier lecture, that state assignment is done in such a way that either area is reused or delay is reused in the earlier designs. Now, since power is one of the most important design parameter, and now we can use state assignment for reducing the power consumption. In other words, you can use it to reduce switching activity. And so, the basic approach, basic requirement here is to do encoding such that the dynamic power is reduced. So, an objective function gamma is decided, which can be minimized, where gamma is equal to summation of p I j into w I j for all transitions, where p I j is the probability transition from state S I to state S j, where w I j is the weight representing the activity factor. So, we shall try to minimize this objective function, and that will essentially reduce the that switching activity in the finite state machine. Let me illustrate this FSM encoding for reducing power dissipation with the help of a simple example. Consider a sequence detector that produces a 1 when 5 ones appear sequentially at the input, and let me draw the state transition function of the finite state machine. It can start with, you can start with state S1, and it has to detect the occurrence of 5 ones. So, as long as it is in 0, it can remain in the state S1. So, it will produce 0 with input 0, then it will go to state S2 when a 1 occurs. So, by producing 0, and it will go to a state S3 if another 1 occurs. However, if a 0 occurs, then it will go back to state S1, that means 0 by 0. And similarly, from state S3 it will again go to state S1 if a 0 occurs. So, 0 by 0, that means output is 0 for the input 0 input. Now, it will go to state S4 again if another one comes. So, 1 0, and then it will go to state S5. We will require 5 states for the occurrence of 5 ones, 1 2 3 and 4 1, and if a 0 comes again, it will go back to, in this case it will go back to 0 by 0, and in this case when it is in state S5, irrespective of whether a 1 or 0 comes, it will produce whenever 1 comes it will produce 1, and whenever 0 comes it will produce 0. So, it will go back to state S1. So, this is the state transition function of this finite state machine, which detects a sequence, detects occurrence of 5 ones, and whenever 5 ones occurs, as you have seen, it produces a 1. So, in this case we can do state, you can perform state assignment, and let us consider two different state assignments, and assignment 1. Okay, let me show it here. So, this is the assignment 1, where S 1 is given 0 0 0, S 2 is given 1 1 1, S 3 is given 0 0 1, S 4 is given 1 1 0, and S 5 is given 1 0 1. So, this is the encoding state assignment that is done in assignment 1, and in assignment 2 for the same states different codes are given. For S 1 0 0 0, S 2 0 0 1, S 3 0 1 1, and S 4 0 1 0, and S 5 is 1 0 0. And in this particular case, the switching activity, transition activity, that parameter that I have told earlier, gamma value for this assignment is 10, and for this assignment is 5.5. Let me show it how I have obtained that. This corresponds to assignment 1, and let me write down another table. This corresponds to assignment 2. As you can see, there are 9 possible transition, 1, 2, 3, 4, 5, then 6, 7, 8, 9. 9 possible transitions. So, one is your S 1 to S 1, another is S 1 to S 2, then S 1 to S 1 to S 1 to S 1, S 1 to S 2, then S 2 to it can go to S 1, and S 2 to it can go to S 3, then S 3 to it can go to S 3 to S 1, then S 3 to it can go to S 4, and from S 4 it can go to S 1, or S 4 it can go to S 5, and from S 5 it always goes to S 1. So, these are the 5 possible transitions, and let us see what is the switching activity for these two assignments. So, whenever it goes from S 1 to S 1, the probability of transition is 0.5, 0.5, and since for the code here, as we have seen, the codes are, in this case, is 0 0 0 and 1 1 1. So, the switching activity, I mean factor from S 1 to S 1 is 0, that means it will be 0. So, it will be 0.0. Whether from S 1 to S 2, when it goes, probability of transition is 5, and switching activity is 3, because this is 0 0 0 and here it is 0 0 1. So, it will be 1.5. So, in this way, from S 2 to S 1, the for the code for S 2 is, as you have seen, 1 1 1. Let me show it here itself, where you have got all the codes as well as the transitions. So, you can see here, whenever it goes from S 1 to S 2, probability is 0.5, and since it is going from S 1 to S 2, there is no transition. So, it is there is no switching activity. So, it will be 0, and S 1 to S 2, the number of transitions is 3 and probability is 0.5. So, 0.5 into 3 is 1.5. On the other hand, for this code you can see the Hamming distance is only 1. So, transition is only 1. So, 0.5 into 1 is 0.5. So, for this transition, for assignment 2, the transition activity is 0.5. Similarly, from S 2 to S 2, S 2 to S 1, S 2 to S 1, the S 2 to S 1, in this case transition activity is 3. So, for assignment 1, 0.5 into 3 is 1.5, and here it is 1 into 0.5, 0.5. And similarly, from S 2 to S 3, S 2 to S 3, here the number of transition is 2. So, 2 into 0.5 is equal to 1, and in this case S 2 to S 3, number of transition is only 1, 0 to 1, other bits do not change, and so it is 0.5 S 2 to S 3, and S 3 to S 1, S 3 to S 1, in this case the number of transition is 2, and in this case number of transition is also 2. So, S 3 to S 1, S 3 to S 1, the number of transition is 1. So, it is 0.5, but here it is 2, S 3 to S 1. So, it is 1, 0.5 into 2 is 1, S3 to S4, S3 to S4, in this case S3 to S4 number of transition is 3. So, 3 into 0.5 is 1.5, and so in this way you can find out for all these transitions, and for from S5, as I have told, it always goes to S1. So, you can see from S5 to S1 either for 0 input or for 1 input it will go to S1. So, probability is 1, and in this case it goes the number of transition is 2. So, 2 into 1 is 2, and on the other hand in this particular case 0 0 0 and this is 1 0 0. So, the number of transition is 1, 1 into 2, 1 into 2 is 1. So, 1 into sorry this is 0.5 plus 0.5 1 into 1. So, number of transition is 1. So, it is 1. So, we have taken into account the possible all possible transitions and multiplied with the probability along with their transition weightage, that is Pij and Sij, which I have already mentioned, this gamma Pij into Wij, and found out this table. And if we take the summation, we get gamma is equal to 10 for the first assignment, and for the second assignment it is 5.5. So, obviously, this assignment 2 is superior. So, this illustrates that by doing a state assignment you can reduce the transition activity of a finite state machine. And I am although it cannot be claimed that this particular assignment is the best one, but because this state assignment is a NP complete problem and you have to find out all possible assignments to find out which one gives you minimum transition activity. But this is just an example to illustrate that this particular assignment is reducing the transition activity to 5.5. And obviously, the dynamic power dissipation for this assignment will be about 55% of the previous case for this assignment. Okay. So, we have discussed the state assignment. Now, we shall come to another important concept, that is FSM partitioning. Again, this was introduced by Benini and his colleagues. So, here the idea is to decompose a large FSM into several smaller finite state machines with smaller number of state registers and combinational blocks. And only an active FSM receives clock and switching inputs, and the others are idle and consume no dynamic power. So, in this case, as you can see, this is the original finite state machine, and we can say this finite state machine, this state transition diagram, this particular path corresponds to the main loop, main program, and this can be considered as a kind of subroutine. So, this from here it can go to this subroutine with starting state T 0, and it can remain in this subroutine for some time, and then of course, it will return to the main process. So, you can see this particular this is a large FSM, it can be decomposed into 2 FSMs, and by adding 2 intermediate states, as you can 2 additional states. So, we have introduced 2 states SW22 in the main subroutine main program, and in the subroutine part we have introduced another state TW0. So, these 2 states actually leads to kind of transition from this machine to another machine, that means the activation of one machine to another machine. So, normally when this FSM this particular FSM is running, this particular FSM remains in the idle state. Similarly, when this particular FSM second FSM is running, the main FSM remains in idle state, and of course, this transition from idle condition to active condition take place through these 2 states SW22 and TW0. That means, when the machine can go can send signals to this FSM, and it can go to this subroutine, and this can become active, and this can remain in the idle state. So, we find that in this case by decomposing a large FSM into a number of smaller FSMs, you can save power, because at a time one of the FSMs will remain in active conditions, others will remain in idle conditions. And however, these FSMs may be interacting with each other. As we have seen, they will send signals. One FSM can put another FSM to active condition, or can put and whenever an active whenever it goes from one FSM to another FSM, obviously it will go to idle state and the other FSM will become active. So, that is what will happen in this particular case. So, this is illustrated with the help of a simple example by decomposing a single FSM into two FSM, but you can have several you can decompose into several FSMs, and basic idea is that you can identify a large FSM and include and find out smaller subroutines, and which have high probability of transitions, and then you can divide them into several FSMs in this way by adding some extra states. So, these addition of states will obviously require some additional hardware, but since one of them will be active at a time, they will be saving in power dissipation. So, that means with additional area you are able to reduce the switching activity in this FSM partitioning. So, we have discussed FSM partitioning, and this is the third technique that can be used in the synthesis of finite state machines to reduce switching activity. Now, we shall consider another very important concept that is used to reduce switching activity, that is called operand isolation. What is operand isolation? Operand isolation is a technique for power reduction in the combinational part of the circuit. So, in a combinational part of a circuit, you can reduce power dissipation. So far, we have discussed about power reduction in sequential circuits or resistors. Now, we shall consider how power reduction can be done in combinational circuit, and in this case the basic concept is to shut off logic blocks when they do not perform any useful computation. So, in this case we shall find out the condition when it is not doing useful computation. For example, this particular adder is producing some result and it is receiving inputs A and B, and this result is loaded into a resistor shown by D, and only when S1 is 1 and S2 is 0. That means, when this condition is satisfied, only then the output of this adder is loaded into this resistor, otherwise it is not used at all. That means, if we consider three possible four possible conditions, say S1, S2 can have four possibilities 0 0, 0 1, 1 0 and 1 1. Now, we find that when S1 is 1 and S2 is 0, only during this condition the output of the adder is loaded, output of the adder is loaded into the resistor. So, this is happening only when this is the condition. That means, the probability of loading the output of the adder into the resistor is only 0.25 or 25%, because out of 4 possibilities only in one possibility the output is loaded. That means, if you can prevent the inputs to reach the adder during the other conditions, then there will be no unnecessary consumption of power in the adder for these three conditions. Only when the S1 is 1 and S2 is 0, then operands can be loaded into the adder and it will do the computation and result will be loaded. So, this is the basic idea. So, shutting off is done by not allowing the inputs to to toggle the clock cycles, toggle in clock cycles when the block output is not used. So, this is the basic idea, and let us see how this is realized. So, the output of the adder is loaded into the latch when S1 is 1 and S2 is 0, as I have explained. So, to perform addition only when the output of the adder is loaded into the latch, an activation signal AS is generated to isolate the operands using AND gates. So, you can see a simple hardware is shown. This is the adder AND gate and an inverter which can generate the activation function, and you can see these operands A and B are ANDed, although only 2 ANDs are shown. Obviously, if it is n bit, you will require n 2 AND gate, you will require 2 AND gates for each bit. So, you will require 2 n AND gates to apply the input to this adder, and you can see this activated signal is active only for S1 is equal to 1 and S2 is equal to 0, and only then these two operands will be applied to this adder, and obviously, the signal will go to this point. For all other conditions, inputs are not allowed to reach this adder, and obviously, unnecessary computation is not done and unnecessary power dissipation do not take place. However, whenever you do operand isolation, it reduces power, it introduces timing, area and power overhead. As you can see, if this particular adder is in the critical path, then addition of these AND gates will introduce some delay. So, this may disturb the timing conditions, and obviously, it will also add some area. You are adding this activation signal hardware, and also you are adding these AND gates. Obviously, this will add to some area and power overhead. So, here the trade off is the power saving that is achieved by using operand isolation is more than the power that is consumed by the hardware that generates the activation signals and the additional hardware that you are using. Obviously, this trade off has to be satisfied, otherwise it will not have any benefit. So, you have to find out this condition using very simple hardware, so that this trade off is satisfied, and obviously, you are adding some additional area to achieve reduction in the power dissipation. So, it is you are trading area for lower power and by reducing the switching activity. So, this is the technique of operand isolation. Now, we shall consider another very interesting technique, that is called pre-computation. So, pre-computation is a technique where you perform computation in which selective computation of the output values is done one or few cycles in advance using a much simpler circuit than the original circuit. So, your original circuit, which may be performing very complex operation, say it may be performing multiplication of n bits, addition of n bits, or it may be performing something more complex function. So, you will identify some simpler hardware, and which will do some pre-computation little in advance, and then what you will do, you will use this pre-computed values to reduce switching activity in subsequent cycles. That is the basic idea of pre-computation, and pre-computation is done by simpler circuit, as I have told. And to illustrate this example, let us consider a combinational logic block sandwiched between two resistors R1 and R2. So, this is a simple generalized circuit to illustrate the concept of pre-computation. So, here is a large combinational block which is receiving input through a resistor R1 and it has got enable signal E1, and output is generating is F through another resistor R2 which has enable signal E2. So, this is the original hardware. Now, pre-computation can be done by adding two additional hardware much simpler than this combinational logic block G1 and G2. G1 is 1 when F1 is 1. So, that means this combinational circuit, when it is 1, this G1 is 1. So, by using a very simple hardware, you are able to find out that, and G2 is 1 when f is equal to 0. So, G1 is equal to 1 and G2 is equal to 0 when this combinational circuit is 1 or 0. Now, what you can see, this you can find out by using simpler hardware. So, these outputs from G1 or from G2 can be channelized to the output depending on the input combination. That means, which condition is satisfied, whether this condition is satisfied, G1 is equal to 1 for when f1 is equal to 1 or G2 is equal to 1 when f is equal to 0, and that can be transmitted sent to this output. And these two signals, these two outputs G1 and G2 can be used to generate some activation signal for enabling this latch or resistor R1. So, that means, you can disable this input to reach when computation is done, when either this is 1 or this is 1. That means, when G1 is 1 or G2 is 1, you are disabling this input to reach this combinational block, and in those situation outputs you are taking from the output of G1 or G2 instead of taking the output from this combinational logic block. That is the reason why you are using this additional hardware to take outputs either from the output of G1 or from the output of G2, and that is taken out through another resistor R2 which has enabled signal E2. Now, this particular precomputation can be illustrated with the help of a simple example, very simple but interesting example. You are familiar with the function of comparator. You are performing comparison of two numbers a and b. So, it has both a and b are of n bits. So, a n, b n, a n minus 1, b n minus 1, n minus 1, a n minus 2, b n minus 2. In this way, it is up to a 1 and here you have got b 1. So, both a and b are two inputs to a comparator. So, this comparator will be receiving normally two inputs a and b, maybe through two resistors a and b, and it will perform the comparison a greater than b or not. Now, you can see whether a is greater than b or not, that can be found out from these two bits if they are 1 0 or 1 1. That means, suppose a n is equal to 1 and b n is equal to 0, then you know that the number a is greater than b without looking into these bits, the remaining bits. Similarly, if a n is equal to 0 and in this particular case a is greater than b, and when a n is equal to 0 and b n is equal to 1, that implies b is greater than a. So, you can see these two conditions can be found out without looking at these bits, the remaining bits. These most significant bits are sufficient to find out the conditions. However, when a n is equal to 0 and b n is equal to 0, or a n is equal to 1 and b n is equal to 1, in these two cases obviously, whether a and b is greater, a is greater than b or b is greater than a, for that you have to consider, you have to take into account the other bits. So, in this way from this you can say that you can do pre-computation with the values of a n and b n, and whenever a n is equal to 1, b n is equal to 0, you know that a is greater than b, and so you need not apply the remaining bits to the comparator. Similarly, when n is equal to 0 and b n is equal to 1, then also you know that b is greater than a. So, you need not really apply the remaining bits to this comparator, and you can save power consumption. So, this is the basic idea of this precomputation illustrated with the help of this comparator example. So, here you can see the circuit that can implement it very easily. So, a n and b n are applied to a resistor R 1 and a n minus 1 to a 1 and b n minus 1 to b 1. These inputs are applied through a separate resistor with a enable signal E 1. Now, this signal E 1 is generated which is a function of a n and b n. So, this is enabled only when a n and b n are 1 are same. That means, when a n and b n are same 0 0 0 1, only then these bits n minus 1 to a 1 and b n minus 1 to b 1 are to be applied to this comparator to find out whether a is greater than b or b is greater than a. In all other situations, that means, when a n is equal to 1 and b n is equal to 0 or b n is equal to 1, a is equal to 0, then you can prevent these bits to be applied to this n bit binary comparator. So, this is what is done with the help of this hardware, simple hardware. So, a simple exclusive OR gate is used to generate the enable signals. That means, whenever both of them are 0 0 or 1 1, I mean then this 0 0 or 1 1, only then this enable signal is generated, otherwise this signal is 0 and output is not applied. And then you take the final output from another resistor R 3. So, here in this example, precomputation function is a n exclusive or b n, which can be realized by an XOR gate, simple circuit. So, in this case, disabling of a subset of inputs takes place. So, earlier we have seen in the earlier case, you are able to disable the entire set of inputs. That means, all the inputs are disabled. So, this is the case where the complete disabling of the inputs are taking place. But in the example that we have illustrated, comparator example, only a subset of the inputs are disabled from reaching the inputs. So, you can obviously the saving will be much more in this particular case, but it may be little complex. You will require little complex hardware to identify these conditions and generate the activation hardware for this particular latch. On the other hand, in this case, although you are able to disable a subset of inputs, there will be significant saving in power dissipation in this comparator circuit, and the activation circuit is also very simple in this particular example. So, the example of precomputation has been shown in this with the help of this comparator, and these topics I have taken from these two references, one by Anand Raghunathan, Niraj Jha and Sujit De, I mean a book written by them, high level power analysis and optimization published by Kluwer academic publisher in the year 1998, and another reference is also a book edited by Christian Piguet, and the book is Low Power CMOS Circuits Technology, Logic Design and CAD Tools, published by Taylor and Francis in the year 2006. So, I can conclude this lecture by summarizing what we have discussed today. First of all, I have discussed about 3 techniques for reducing switching activity in finite state machine. The first example was in FSM. You can use gated FSM. You need not apply the clock all the time. You can identify conditions, idle conditions, and by finding out idle condition, you can get the clock and save switching power dissipation. Second was encoding. You can do state encoding such that the switching activity is reduced, and then we have used another technique that is called that is essentially a technique where you do FSM partitioning. And after that, with the help of these three techniques, you can reduce power dissipation in finite state machines, and in combinational logic blocks also you can reduce power dissipation by using two techniques that are two techniques, and these two techniques are, number one is operand isolation, and second one was pre-computation. So, in these two cases, when you are driving a large combinational circuits, you can inhibit the input to reach these combinational circuits and stop unnecessary transitions. So, with this let us conclude our lecture. In the next lecture, we shall discuss about various architectural techniques that can be used to reduce switch can be used to minimize the switch capacitance in a circuit, and also we shall discuss about different logic styles that you can use to reduce power dissipation. Thank you.